Okay, so we start from where we are left in the last class. Okay, we are discussing about the reflector antennas. So I'll just do the presentation. So we stopped it here only, reflector antennas. Okay, so we will continue from here. So reflector antennas are basically the reflectors. One source will be placed, and from that source, the rays will come, and the reflecting surface will reflect it into a particular direction. It is basically reflectors. So I think yesterday we have just seen these slides and all we have discussed yesterday. Okay, this also we have discussed the plane reflector and corner reflector. Okay, the feed you can see from the feed is the source. Okay, from the feed rays are coming and it is getting reflected by the reflecting surface. Okay, so plane reflector, it cannot concentrate waves into a particular point. So, but where in the corner reflectors, it can concentrate waves into a particular direction. Okay, so that is the major difference between a plane reflector and a corner reflector. Okay, so this is all we have seen yesterday. Simplest form uses plane reflector to direct electromagnetic energy in a desired direction, but it is difficult to collimate the beam in the forward direction. So, for better collimation, we are using corner reflector. Just placing two plane reflectors at an angle, we will be getting corner reflector. Okay, and these things are very familiar with you. Like I think you might have seen this also. Have you seen an antenna like this? Have anybody seen an antenna like this? This is just a reflector. Okay, at the end, at the left end, you can see one reflector is placed. Okay, so this type of antennas used to be there while this terrestrial communication was there, like terrestrial TV transmission of from Trivandrum, Doordarshan Kendra, one transmission was there. I think now also it is there that we used to capture with this kind of antennas. Normally Yagi-Uda antenna, but Yagi-Uda antenna with the reflector, this one. Okay. So you can see the leftmost side, one reflector is there. This is conical, sorry, corner reflect. This is a classical example of corner reflector antenna. Okay. So we'll move on to the next slide. We'll move on to parabolic reflector antennas. Okay, as the name suggests, here the reflector will be of parabolic shape. Okay, so that is the difference here. We have seen plane reflector and corner reflector. Now we are going to see parabolic reflector antennas, and these are the most commonly used type of antennas. Parabolic reflector type of antennas. All of you must have definitely seen at least one or two antennas like this. Okay, so that we are going to study. Okay, so parabolic reflector antennas. The overall radiation characteristics of a reflector can be improved if the geometrical shape is parabola. That is the idea behind this parabolic reflector antennas. The overall radiation characteristics of a reflector can be improved, provided the geometrical shape is parabola. You will see how. Okay. If a beam of parallel rays is incident upon a parabolic reflector, the radiation will converge at a spot which is known as focal point. So you can imagine of a parabola. Okay, you know what's a parabola. Okay. So you just take the shape of a parabola and imagine the rays are incidenting upon that parabola parallelly. Okay, parallel rays are coming and incidenting upon the parabola. What will happen? Parabola, basically parabolas are having focal points. Okay, so the incident rays the parallel rays which are incidenting upon the parabola will converge at a spot or which converge at the focal point of the parabola. That is the idea. Okay, I'm placing a parabola here, and waves are coming and incidenting upon this. All those waves will be concentrated at a particular focal point. Okay. So we are using it for transmission also. Suppose I am placing a parabolic antenna here, parallel rays are coming, it will incident upon this and that will converge to focal point. Okay. So in the same manner, if a point source is placed at the focal point, I am placing my point source at the focal point of the parabola. Okay, then what will happen? The point source will radiate electromagnetic radiations. That rays will incident upon the parabola, and the parabola will reflect that into parallel waves. Okay, the first case was reverse. That means parallel waves are coming and incidenting upon the parabola, and parabola was focusing all that rays into focal point. Now what we are doing? We are placing our source at the focal point so that the source will radiate. Source radiates the electromagnetic waves, and those waves are incidenting on parabola and they are traveling as parallel waves. Okay. So the rays reflected by a parabolic reflector will emerge as a parallel beam. Okay. The rays that emerge in a parallel formation are usually said to be collimated. So parallel, instead of a spherical wavefront, a parallel wavefront we are getting, and it is said to be collimated. Okay. The radiation pattern of an antenna employing parabolic reflector has a very sharp major lobe accompanied by a number of smaller minor lobes. Okay, that we can understand, because if I am placing a parabola in this direction, if I am placing a parabola in this direction, most of the rays will come and reflect in that direction only. Some rays can go outside of the parabola and they can travel in other directions. So the major lobe will be very sharp. Okay, the major lobe will be very sharp, and it will be accompanied by a number of smaller minor lobes. So here it is shown. Okay, as the transmitter or receiver is placed at the focal point. Here it is shown as the case of transmitter. You can see the transmitter, this is a point source placed at the focal point of the parabola. Okay. So this parabola is aimed to transmit waves in this direction. This arrow mark is there. This direction only it is transmitting the waves. So the point source will be kept at the focal point, and the point source will radiate randomly. Okay, it will radiate, and most of the rays will fall on the parabola. You can see rays are falling on the parabola and getting reflected. Okay, since our reflector is parabolic reflector, they are reflecting. After reflection, you can see is a plane wave. The wavefront is plane. So plane waves are coming out of the parabolic reflector. So this is the radiation pattern. You can see major lobe is very sharp. Minor lobes are there since some rays can go outside the parabola. Okay. So this is the geometry of a parabolic reflector in transmitting mode. What if it is in the receiving mode? Receiving mode also same. There is no difference. The only difference is the arrow mark will be reversed. In receiving mode, plane waves are coming and incidenting, and they will converge into this particular point or the focal point. That is the only difference. Okay. So we can use it either as a transmitting antenna or as a receiving antenna based on our requirement. Okay. So this is the geometry of parabolic reflector in receiving mode. You can see plane waves are coming here. Plane waves are coming, incidenting upon the parabola, and all are focusing on the focal points of the parabola. Okay. So that is the only difference here. That is the only thing you need to understand. Okay. So if a feed antenna is placed at the focus, feed antenna means our source. Okay. The source which feeds the signals. If a feed antenna is placed at the source, at the focus, All the waves are incident on the reflector and they are reflected back, forming a plane wavefront. The main purpose of a parabolic reflector is to convert a spherical wave into plane wave. That you can see. See here, I was placing my feed antenna or my source at this focal point. Here, the wavefront is spherical, means it is equally radiating in all directions. But after getting reflected by a parabolic reflector, you can see the wavefront is plane. Okay, so we can convert the spherical wave into a plane wave. Okay, here you can also see the feed is front. The antenna feed is front fed. Means I have to keep my point source or my feed antenna in front of the reflector. Then only it will reflect. So we can say that it is front fed. I am keeping my point source or my feed antenna in front of the reflector. We cannot keep it here. Okay, I have to keep it here only. So that will constitute some disadvantages. The disadvantage of the front fed arrangement is that the transmission line from the feed must usually be long enough to reach the transmitting or the receiving equipment. Okay, one transmitting equipment will be there. From that only we are getting the signals. That signal is only transmitted by the point source. That point source we have to keep, or point source or feed antenna that we have to keep in front of the reflector. So from the transmitting equipment to front of the reflector, that feed should be having that much length. Okay, that is the feed signals are coming from a transmitting equipment. From that equipment up to in front of the reflector, that much length should be there for the feed element. Okay, that usually led to transmission loss because that much length is there for the transmission antenna or transmission element or feed element. For due to that, some transmission loss will be there. Okay, because from the source or from the transmitting element, the signals has to reach up to that particular point, focal point of the parabola. From during that transmission loss can happen. Okay, then next, antenna placed at the focus of a paraboloid is known as feed radiator or primary radiator, and its radiation pattern is known as primary pattern. That is a normal pattern. One antenna we are placing at the focal point. Okay, that antenna will be having a radiation pattern. That is the primary radiation pattern. That will be radiating spherical wavefront. Okay, the parabolic reflector is known as the secondary radiator. Why? Because the parabolic reflector is not radiating on its own. It is just reflecting the waves which are radiated by the primary radiator or our feed antenna. Okay, so the parabolic reflector is known as the secondary radiator, and the radiation pattern of the entire antenna system is called secondary pattern. Okay, it's just the terms you need to remember. It is seen that some of the desired rays are not captured by the reflector, and this constitutes spillover. That I already told you. Like if I am placing my feed antenna or my primary radiator at the focal point, some rays can escape. Some rays will go outside of the parabolic reflector. So that constitutes spillover. While receiving, spillover increases noise pickup. Okay. So while at the receiving mode, if spillover is there, means we will not get a complete message. So that we can term it as picking up of noise. Some radiation from primary radiator occurs in the forward direction in addition to the desired parallel beam. This is known as back lobe radiation. But I will tell you what is back lobe radiation. See, here I am placing my primary antenna or my point source or primary radiator at the focal point. Okay, it is radiating. It is radiating towards the parabola. Okay, and it can even radiate backward direction also. It can radiate. You can see B. This B, right? That is the radiation directly from the point source. Likewise, it can radiate in all direction backward also. Okay, it is not necessary that it should radiate towards the paraboloid itself. It can radiate towards backward direction also. Okay, that is a problem here. Okay, that is known as back lobe radiation. Those radiations are not reflected by the parabola. Instead, they are the back lobe radiation of the antenna itself. You might be remembering we have studied about back lobes and all, front lobe, back lobe, side lobes and all. Okay, this is that thing on the back lobe radiation. Back lobe radiations are not desirable as it can interfere destructively with reflected beam. Okay, that is a main thing. The reflected beam means the reflected beam will be having a phase difference. Okay, the reflection will cause a phase difference. Reflection will create a phase difference. So the reflected wave will be having a phase difference. So if back lobe radiations are there, back lobe radiations are not reflected. They are directly coming from the primary radiator or the point source. Okay. So if they are interfering with the reflected waves, what will happen? There will be a phase difference between the waves. This phase difference can interfere destructively. So as a result, what will be the result of destructive interference? What will be the result of destructive interference? The wave will disappear. Waves will destructively interfere and they will disappear. It will finally result in loss of the data. Okay, understood. These are simple things. You can just go through that. That is simple things. Okay, this is the equation for bandwidth between first nulls. 140 lambda divided by d degrees. Okay, that is the bandwidth, beamwidth between first nulls. Where lambda is the free space wavelength or wavelength of the signal we are using, and d is the diameter of aperture. Yeah, aperture diameter of the parabola. And half power beamwidth, that is 70 lambda by d degrees. Directivity d is given by 9.87 d square by lambda square. Power gain when a dipole antenna is used. Dipole antenna is used means a dipole antenna is used as a primary radiator, or the point source will be a dipole antenna. In that case, power gain is 6.4 into d square by lambda square. Okay, just remember these equations in case you have to write it while explaining the parabolic reflectors. Okay. So now we are moving on to a very important thing, that is feed systems. Feed antenna, you already know what is feed antenna. Feed antenna is the antenna we are placing at the focal point, or we are placing in front of the reflector. This is the feed antenna, or it is also called as the primary radiator. Okay. So there are different type of feeds, different methods to place the feed antenna, and different methods to place the reflectors with respect to feed antenna. So that are called as feed systems. Okay. Parabolic reflector antenna consists of two components: reflector and a source of primary radiation at the focus. Okay. The source is called as feed. Okay. All these things we have seen already. An ideal feed would be that radiator which radiates towards reflector in such a way that it illuminates the entire surface of reflector and no energy is radiated in any other direction. Okay, that is an ideal feed. What should be the characteristics of an ideal feed? An ideal feed, we are placing at the focal points, or if we are placing in front of the parabolic reflector, all the radiation should fall on the entire surface of the reflector, and all of that should be reflected. So no energy is wasted or no energy is radiated in any other direction. That is an ideal feed. Okay, that is not practically possible. So we are moving on to different feed techniques. Okay, first one is axial or front feed. Okay. Axial or front feed system. See, as the name suggests, This is the most common type of feed, with the feed antenna located in front of the dish at the focus on the beam axis itself. Okay, this we have just discussed. This is the basic case, general case. Okay, feed antenna will be located in front of the dish, or in dish means parabola. Okay, in front of the parabola or in front of the dish, and it will be at the focus on the beam axis. Okay, pointed back towards the dish, and that will be pointed back towards the dish, so that it should radiate into dish only. Okay, this is the feed antenna. Here you can see the feed antenna is supposed to radiate into this dish or this parabolic reflector only. No other radiations, in order to avoid any backlobe radiations and all. We are placing the radiator or feed antenna in such a way that it is supposed to radiate towards this parabolic reflector only. Okay. A disadvantage of this type is the feed and its supports block some of the beam. Okay, that you can just understand by seeing this. See, here feed antenna is shown in green color. Okay, and the supports are shown in blue color. Feed antenna should be supported by something. It cannot hang from space like that. Okay, we have to give a support for the feed antenna. Okay, so these blue lines are the support of the feed antenna, and feed antenna is placed here. Okay, and we are supplying feed antenna with the signal we want to transmit, and the feed antenna will be oriented towards this direction, and it transmits towards this direction, and from all those waves they will be reflected back by the parabolic reflector. So what is the problem here that can happen? See, here the supports are there in blue color, and feed antenna is also there in green color. Okay, all these are in front of the reflector. So while the waves are getting reflected from the reflector, these are obstacles for them. Okay, this support system and feed antenna, they will block some of the signals. Okay, so that limits the aperture efficiency to only 55 to 60%. That is the main disadvantage here. Everything was okay, but the support system and feed antenna, that can block major part of the signals, or a part of the signals can be blocked by support system and feed antenna. Okay, so that the aperture efficiency will fall down to 55 to 60%. Okay, so you might have seen this type of antennas. Have you ever seen this type of antennas? Have you ever seen? Have you seen the dish antennas? All the dish antennas, all dish antennas, like satellite communication. That time no cable was there. When satellite communication started, all of the houses used to have this dish antennas. Okay, so those dish antennas were making use of this type of feed. Okay, so if you remember, okay, I don't know, I will show you one example for that. See, this type of antenna. Okay, have you seen this type of antenna anywhere? Nobody have seen. See, here you can see the support system. These are the support system. 1, 2, 3, 4 legs are there for supporting, and here the primary radiator is placed. Okay, and this can be used for receiving also. Okay, our antennas which we are using in the home and all, they were receiving antennas. There also same problem exists. This supporting system that will hinder the waves which are coming, or waves which are falling on the parabola. Okay, there also same problem will be there. Okay. Yes, at least 1 or 2 people replied. Yes, yes. Yeah, anyway, we will move on to next feed technique. off-axis or offset field. Okay, the problem with our axial field was the problem with the supporting mechanism and the feed antenna, that they were blocking some of the signals. So in order to overcome that, we are doing for an off-axis feed or offset feed. That means the problem with the axial feed was the antenna was located at the axis. Okay, so it has to be supported from four ends. So if the antenna is primary radiator or the main antenna, we are moving out of the axis. Some of the disadvantage can be minimized. Okay. So the reflector is an asymmetric segment of a parabola. So the focus and the feed antenna are located to one side of the dish. That is the thing here. Instead of taking a symmetrical segment of the parabola, we are taking an asymmetrical segment. Okay. Symmetrical segment means the focal point will be at the center of the parabola. So we have to keep our feed element, our primary radiator, at the center itself. Okay. If we are choosing for an asymmetric segment, what will be the difference? The focal point will not be at the center. Okay, focal point will be somewhat shifted, so that we can keep our primary radiator at any of the edges, so that the focal point will be shifted to one of the edges rather than locating at the center. If we are choosing an asymmetrical segment of a parabola, the focal point will be on one of the sides. Our requirement is we have to keep the primary radiator at the focal point. Okay. Since we have chosen an asymmetrical segment, the focal point will be shifted to one of the edges. So that will be located to one side of the dish. There we can place the radiator, primary radiator. Okay. The purpose of this design is to move the feed structure out of the beam path, so it does not block the beam. Okay. It is widely used in home satellite television dishes, which are small enough that the feed structure would otherwise block a significant percentage of the signal. This type of antennas are very, very common nowadays. This DTH, direct to home, and all those mechanisms, Sun DTH and all, they are using this type of antennas. See, you can see the arrangement of axis or offset feeds. This red line is an asymmetrical segment of parabola. Since it is asymmetrical segment, its focal point will be here, located at one edge. Okay. At that edge, we can keep the primary radiator. And this blue is the support for that. It is not at all blocking the beam. Okay. Since it can be supported from one edge, it is not at all coming in the direction of or in the path of the wave. Okay. So that the waves can travel without any hindrance. See, this is the dish. All of you might have seen this. Okay. I think many of them having that in your home also. That is offset feed parabolic antenna. Okay. It is a very commonly used antenna for home televisions and all those things nowadays. So you can see the advancement over the years. Previously in 2090s and all, we were using the antenna I have shown you first, that axial fed antenna. So now we are using this kind of antenna. So we are step by step, we are overcoming the problems. Okay, that's how our science is developing. Okay, we'll move on to next feed technique. This is gas grain feed. Okay. Cascgrain feed. It uses a parabolic reflector, a hyperbolic reflector, and a feed antenna. Okay. Till now, we have seen axial feed and offset feed. In both, we were having a parabolic reflector and a feed antenna or primary radiator. Only these two things we were having. But while coming on to cascgrain feed, we are having a parabolic reflector, a hyperbolic reflector, and a feed antenna. Okay, two reflectors are there: a parabolic reflector, a hyperbolic reflector, and a feed antenna. Okay, two reflectors and a feed antenna. instead of having one parabolic reflector and feed antenna, we are having two reflectors and one feed antenna. In the two reflectors, one is parabolic reflector and another is hyperbolic reflector. Okay. One of the foci of parabolic reflector coincides with the focus of paraboloid. Okay. That means one focus of the parabolic reflector that coincides with the focus of paraboloid. In this, the primary radiator is positioned around an opening near the vertex of parabola instead of focus. We have seen in previous two cases, the primary radiator, we were placing the primary radiator at the focus of the parabola. Okay. But here, the primary radiator is positioned at an opening near the vertex of the parabola. What is the vertex of a parabola? Vertex is the edge. Okay, parabola will be having one edge that is called as vertex. Okay, so there we will place the primary radiator. When the radiations from the feed radiator are incident on the hyperboloid reflector, they are reflected back and then incident on the paraboloid. These incident rays are reflected and propagates as a plane wavefront. Okay, but I will explain. See here, the entire explanation is here. See, this is the parabolic antenna. We are taking a parabola, complete parabola, not an asymmetrical portion, a symmetrical parabola we are taking as a reflector. Okay, and here horn is nothing but a horn antenna. We are using as a primary radiator. Where we will place the radiator here? We used to place the radiator in the focus in all previous cases. But here, instead of keeping the radiator at the focus, we will keep it at the vertex. Okay, vertex of the parabola, you can see this is the vertex, this is the edge of the parabola. Here, we will keep the antenna or primary radiator. Okay, and a hyperbolic reflector we will place here such that the focus of the hyperbolic reflector and focus of the parabolic antenna both should be same. Okay, that is the difference here. This is a parabola with the focus here. This is a hyperbola with the focus here. Both will be having same focus. Okay, so what will happen when primary radiator or our horn antenna radiates? The radiations will fall on this hyperbolic reflector. Okay, and from that reflector, it will get reflected onto this parabolic antenna. Okay, and that will radiate further or that will reflect further, and it will form a plane wavefront. Okay, these techniques are the most modern techniques which we are using for satellite communication and all. So this is cascade feed. Okay, in cascade feed, one parabolic antenna will be there, or parabolic reflector will be there, hyperbolic reflector will be there, and a primary radiator or primary antenna or feed antenna will be there. Okay, the feed antenna will be placed at the vertex of the parabolic reflector. Okay, and the hyperbolic reflector will be placed inside the parabolic reflector in such a way that both foci of hyperbolic reflector and parabolic reflector coincides. Okay, then the feed antenna or primary radiator radiates the signals onto the hyperbolic reflector, from which it gets reflected and fall on the parabolic reflector. From there, it is again reflected and it form a plane beam of wave. Okay, that is the basic idea. So, the advantages: reduction in spillover and minor lobe radiation. Okay, the spillover will be minimum. Okay, so because both the forces of hyperbola and parabola are same, all of the rays which are falling on the hyperbola get reflected into the parabolic reflector itself. No spillover will be there. Okay, spillover means like some signals can escape from parabola. That will not be there. Ability to get an equivalent focal length much greater than the physical length. Okay, it can get a focal length which is much greater than the physical length. Ability to place the feed in a convenient location. That is a very important thing because the feed will not block the signals. We can place the feed outside of the path of the trace. Okay, that is a very convenient location. Then capability for broadening the beam by moving one of the reflecting surfaces. Okay, that we can achieve. You can just imagine if we are moving the distance between these two reflectors, we are increasing, the beam will get broader and broader. Okay, so more accessible for servicing and adjustments because it is main servicing will come in the feed antenna only. Because after apart from this feed antenna, we are just having two reflectors. There is nothing much to service in that. Reflectors will be having some reflecting surfaces. That's it. And the main servicing and adjustments will be happening with respect to the feed antenna or primary radiator. That is outside this arrangement. So it is easy to service and adjust that. Okay. Disadvantages: some of the rays are obstructed by the secondary reflector. That's a disadvantage. That you might have noticed. Okay. Here the reflector is there. So this some of the rays can be get obstructed by this. Okay, that is there. So large paraboloid is expensive. If you are going for a very large paraboloid, it will be quite expensive. Polarization of the wave is twisted 90 degrees when reflected by parabola. Okay, that is also there. So it can interfere. But since the waves are plane waves, the chance of interference are less. So it's just a disadvantage. You can just say like, okay. Then applications. It is used when it is required to keep the primary antenna in a convenient position. The primary radiator, if we want to keep that in a convenient position, we can go for this because the primary antenna is coming outside of this arrangement. Okay. It is used when short transmission line is to be used because the primary antenna should not come in front of the reflector. Okay. So we can use a very short transmission line. Transmission line need not be much larger. From the transmitting equipment, directly we can transmit by using an antenna, using a horn antenna as we have seen already. Okay, it's used for low noise receiver application. Low noise receiver applications. Okay, such applications. See, this is Cascade antenna. It is located in Sweden. Okay, and here you can see, and it is a very modern antenna. You might have seen this in some television programs or somewhere. Okay, it is used for mainly for satellite communication. See here, this is the feed antenna or primary radiator. Okay, here you can see paraboloid reflector. Okay, paraboloid reflector is there. Sorry, hyperbolic reflector is there. Hyperbolic reflector. So this will radiate into this, and this will reflect waves into this main parabolic reflector, and then it will radiate into space. Okay, for reception also. For reception, what will be the thing? From space, waves will come and incident upon this. It will reflect and concentrate waves into this. Okay. So this will further concentrate waves into this portion. Okay, so we will be getting a better reception. So next one is the Gregorian field. Okay, similar to Cascadian design. This is Cascadian design is similar to Gregorian field, but only the difference is that except the secondary reflector is concave. Okay. In the Cascadian field, you can see the hyperbolic reflector is convex. Okay, and here you can see the hyperbola is concave, or hyperbolic reflector is concave reflector. Okay, that is the only difference. All other things are same. Feed we are giving here at the vertex of the parabola. Here we are giving the feed, and it will fall upon this. And so you can see two rays they are shown. It is falling on this, and it will be reflected back to this, and plane wave is formed. Likewise, here also this blue line it fall upon this at this point, hyperbola concave reflector. Then from that, there it is getting reflected into this parabolic reflector and fall from this place. Eventually, they form a parallel beam. Okay, so that is the thing with Gregorian feed. Okay, so this is a offset Gregorian antenna. It is used in Allen Telescope Array radio telescope at University of California. Okay, University of California. Can you say is there any difference with Gregorian feed and this particular antenna? See, in Gregorian feed, the hyperbola was located at the center. Okay, like in Cascadian field. Here, this hyperbola, this is a convex hyperbola. This is located at the center. Okay, so in the classical Gregorian field, this concave hyperbola is located at the center. Okay, that is a classical thing. So, what is the difference between this particular antenna and a classical Gregorian field antenna? What is the difference? Just observe and say the difference. No difference. What is the difference? Concave, that is the difference between yes. Secondary reflector, side level. Yes, correct. That is the correct thing. See, you can see in classical Cascadian feed, this is the Cascadian feed. Okay, in Cascadian feed we are using concave. Where in sorry, this is the Gregorian feed. Sorry, this is the Gregorian feed. In Gregorian feed, we are using concave. In Cascadian feed, we are using convex. That is the only difference. Okay, all other things are same only. So this is a Gregorian fed antenna. See, you can see why it is a Gregorian fed antenna. This is concave. Okay, it is concave. Inside is hollow. Okay, this is concave. From while looking from inside, this is concave. Okay, so with that we are calling it as a Gregorian antenna. If it was convex, convex means it will be like this. Okay, if it was convex, it should be Cascadian antenna. Since it is concave, it is Gregorian antenna. But the difference you can see, this is located on an edge. Okay, so it is called offset Gregorian antenna, like our axial fed antenna and offset fed antenna. In Gregorian fed, we are using offset. That is the difference here. Okay, so that what is the advantage of using this offset fed? What is the advantage? Nobody is listening. Okay, what is the advantage? Can anybody tell? Yeah, beam is not blocked. That is the advantage. Okay, that is the advantage. Okay. I think you people are not at all listening. Like, even I can see a lot of status updates and all those things while my classes are going on. We are just wasting our time. I don't know. If you are listening, it will be good. So that's all with our fourth module. It is almost completed. And for your interest, I will show you one or two things which we are practically implementing. This is called ASIP Observatory. Okay, this is a very big antenna. Okay, it is a reflector antenna located in Puerto Rico. Puerto Rico, completed in 1963. It was world's largest till 2016. Okay, in 2016, China made a larger antenna than this, a larger reflector antenna than this. Okay, this is 1,000 feet in diameter. Okay, the dish surface is made of 38,778 reflected aluminum panels, each about 3 by 6 feet. Okay. And it's supported by a mesh of steel cables. The reflector is a spherical reflector, not parabolic reflector. This is one of the, now it is second largest in the world. Okay, after China's, this is second largest, Arecibo Observatory. It is used as spherical reflector, not parabolic one. Okay, so you can see how big it is, and you can see the feed system. Here, this is the feed system, and this is the dish. Okay, the feed system, it is supported by towers. 3 towers are there for just to support the feed system. Okay. Then this is presently largest, China's 500-meter aperture spherical telescope, or FAST. It is also called as FAST. 500-meter aperture spherical telescope. It is, as the name suggests, it is 500-meter diameter is there for this telescope. Okay, and you can see the field system. Some 1, 2, 3, 4, 5 towers are there, and those towers are supporting the field system here. Okay, so these are the things which are practically implementing, and this FAST, the China's telescope or that antenna, reflector antenna, it discovered the presence of hydrogen out of the Milky Way. Outside of the Milky Way, it was discovered the presence of hydrogen. Okay, so I will show you one video also for regarding that. It is for your, just for the sake of interest. Somebody is interested, they can. Okay, this is about that antenna, that the world's largest telescope or world's largest reflector antenna. It is also a spherical reflector, not a paraboloid.
In southwestern China, engineers are putting the finishing touches on a grand astronomy facility, a half-kilometer wide dish nestled in the mountains that will gather radio signals from the cosmos. FAST, set to be the world's largest radio telescope, is modeled on the second largest dish in the world, the Arecibo Observatory. Started in 2011, the cost of construction for the FAST facility is estimated to be $180 million. Spherical dishes reflect and concentrate incoming waves from a range of angles, but not onto a single point, delivering a distorted image to receivers. FAST is breaking new ground with a design that pulls a section of the dish into a gradually moving parabola. An array of actuators pull a 300-meter section into a temporary shape. This can be aimed at and track cosmic objects as the Earth rotates. The receiver moves in concert with the axis of the parabola. This brings the benefits of a rotating, tilting antenna to a dish that is firmly fixed in place. Single dishes excel at observing point sources like neutron stars and at scanning a multitude of frequencies in the search for extraterrestrial intelligence. When it comes online, the world's largest radio telescope will also catalog pulsars, as well as probe gravitational waves, dark matter, and a recently discovered phenomenon called fast radio bursts.
So that was about the world's largest reflector antenna. Okay, and it is using to collect the radio waves from outer space. Okay, and from other galaxies and all, radio waves are coming, and this by using this, we can collect that. Okay, that is the idea behind that. Okay, so I think with this, our fourth module has been completed, and in the next week we will cover our review of fifth module, and with that, I think we can conclude the syllabus. Okay, so I think that's it. So we can continue our class next week.